Hello, everyone. On behalf of Toyota Connected India, I welcome you all to the 23rd edition of Techceleration conference. This time it's virtual. Before we begin with any introductions about myself, about the speakers, about Techceleration, let's start with a fun exercise. In the question answering forum of the Teams window through which you're looking at me, there are two questions posed. Sort of like two puzzles. Identify those two personalities. The answers will be given in the chat, in the question answering forum discussion place itself. On that note, since now you get familiar with what a question answering forum is, if you happen to know the speakers, if you are friends with the speaker, if you are from the same alma mater as a speaker, do encourage them, give them a lot of appreciation if you find their topic really useful. So now that I have explained how the teams work, and I believe you're able to see the questions. Anita, you can post the questions. Yes. Now they're there. You can answer them while I speak. Techceleration, 23rd edition. So what did we do in the last 22 editions? We've covered topics ranging from Rust, Go, DevOps. An entire theme was on SecOps, InfoSec actually. Then there was an entire Techceleration conference centered on MongoDB. We have had sessions on quantum computing too. There were a session there a couple of years ago, more than 3 years ago, we've had sessions on Techceleration event on classic NLP. Now, back then we did not call it classic NLP. We have had a session on generative AI and large language models. And today we are going to discuss Agentic RAG. 3 speakers are coming to discuss Agentic RAG. Before they begin, there are a couple of definitions that are floating around for Agentic RAG. One is the vector-free long context RAG, wherein you pass a 1,000-page document and the large language model skims through the document like a human would and answer. That definition of agentic RAG is not what we are discussing in the next 3 topics. Personally, I'm not so favorite. I don't find them that very useful in many scenarios that we need. The second one, the definition that we are going to look at is a RAG in which there will be multiple retrievals, multiple LLM API calls where there is a decisioning capability enabled LLM in place in the system, which will do multiple retrievals and multiple LLM API calls. Enough with me hogging the stage. So I'll leave the speakers to explain more about Agentic RAG. And I'm sorry, I did not even introduce myself. I don't think the audience cares, but let me introduce. I am Sandil Kumar. I'm an applied AI and cloud engineer at Toyota Connected India. If you're wondering, that's not an official designation. Before joining Toyota Connected India, I worked with Ford and Latent View. If any of you are from my alumni companies, Virtual Hi-Fi. On that note, I would like to hand it over to SRIHARI. About SRIHARI and I have worked for the last 2.5 years. He's the fashion czar of Toyota Connected India here. So he comes in really fashionable clothes. SRIHARI has actually played multiple roles in his projects. Some of them being a backend cloud developer, a machine learning engineer deploying inference pipelines, of course, applied AI also, which is the Gen AI project. He implemented Agentic RAG, and hence he's delivering the talk on Agentic RAG today. On that note, I would leave the floor to the speakers, starting with SRIHARI. The stage is yours, SRIHARI.
Hi, everyone. Hello, am I audible? I'm audible, right?
Yes, Sri.
Hey, everyone. Good evening. So it's my first ever talk holding a mic. I'm nervous, but I'm really excited to kick off the Techceleration with today's topic, building agentic RAG systems in a production cloud setting. So in this session, we'll go beyond like simple retrieval and explore how we can build intelligent AI systems that can actually plan, act, and adapt in real world environments. So don't mind me if I'm running through the slides. I have a lot to cover given just the 25 minutes. You can always reach out to me post this meet. So before we dive in, I want to start off with a real business use case, something we actually faced in our own organization. We ended up solving it using an agentic RAG system. So let me kickstart the session with a scenario to set the context. So when a new employee joins an organization, day one is like a fire hose. You need to understand internal policies, sensitive project documents, product details, or architecture diagrams and whatnot. And of course, there are KT sessions, but real questions show up later while onboarding tasks are in flight or when SMCs are busy or even a policy which got changed yesterday. So we need answers that are safe, grounded in our docs and available on demand, not just stuck behind calendars, right? So what if a bot could safely retrieve a reason over context, ask clarification questions, and then cite its sources autonomously? Interesting, right? So that's the promise of agentic RAG, not just fetch and summarize, but plan, retrieve, reason, act securely with traceable citations. So I didn't create this demo with a fancier UI. It's just a simpler version, but it shows the power of retrieval, reasoning, and autonomy all working together. So I'll just play the demo and I'll talk over. So this quick demo is the solution of the scenario we just discussed. New employee who just joined, trying to find HR policies and understand his project related documents. Let's see how their day could look if they had an agentic RAG assistant by their side. So I have an AI generated documents on HR policies and few simple companies product related documents called product alpha. I'll quickly show you the documents for reference. So here are the AI generated documents, which I've already integrated and created a chatbot out of it. So let me just shoot the questions to the chatbot. So the first question, it's a straightforward question. It's about a leave policy. The agent is retrieving information from the documents and curating a response. Now, the second question is a product related questions from the one of the documents, but the question is with an ambiguity, like after the firmware update, how do I fix it? So this is where the agentic nature kicks in. As you can see, it looked into relevant documents for the query and it recognizes missing context and asked me 2 to 3 clarification questions. Now let me respond to these. As you can see, the response is being generated after the clarification question. It plans a troubleshooting sequence. The last question, it's going to be a multilingual support. The question is, does the company offer referral bonus? But I've given the query in Spanish. As you can see, the response is being generated in Spanish, but unfortunately, I don't understand Spanish. So I'm going to tell that I don't understand Spanish to the agent. And now the response is being generated in English. But how did it even know to translate the previous response? So the agent has a memory inbuilt in it. So that's a taste of what you can actually build. I've just discussed a particular scenario. While you have many use case, you can actually build a customer support troubleshooting agent, or a product owner would want to understand or gather their Jira tickets, analyze user reports or user feedback. So before we get into Agentic RAG, let's ground ourselves in the basic RAG pattern. So RAG stands for Retrieval Augmented Generation. First, retrieval. When a user asks a question, we don't rely only on what the model already knows. We search a trusted knowledge base, be it company documents or policies or product manuals, uh, anything, right? And pull the relevant snippets out of it. And then you augment it. We need those retrieved chunks into the model's prompt. So we feed those so that it can reason with real current data instead of just pre-training memories. And finally, the generation. So the model produces a natural language answer, ideally with citations or sources references. So together, that's retrieval augmented generation or RAG. It extends an LLM with real-time knowledge, which means your answers stay accurate, grounded, and up to date. So now that we know what RAG is, let's look at how it evolves into something much more capable from RAG to agentic RAG. So let's understand traditional RAG. So it's basically a single query goes to a retriever, fetches relevant chunks, and the LLM generates a response. It works well for direct questions like what's your leave policy, but it's static. There is no reasoning loop. There is no clarifications on if the question requires multiple steps or deeper reasoning, it often breaks down. That's where the agentic RAG comes in. So agentic RAG makes that base, adds a planning and reasoning layer instead of just a retrieve answer. It can actually analyze the query, sets sub goals or plan its next actions. And if more context is needed, it decides again to retrieve or even take actions like calling tools. This happens in repeat unless the generated answer is validated by the agent. So now that we have seen what RAG means conceptually, let's look at what's happening under the hood of traditional RAG system. So for me, it's like a two-phase system. You first prepare and then you start querying it. So we start with our documents. These could be our HR policies or product manuals, be it whatever. The first step is encoding. So each document is broken into chunks and passed through an embedding model, which converts text into numerical vectors to capture semantic meaning. And the step two is upon the encoding, those vectors are indexed in a vector database, or in a simpler words, stored in a vector database. Think of it as a search engine or meaning just keywords. Now the phase two, which is querying. When a user asks a question, the query itself is converted into an embedding using the same model that we used for storing the documents. Second, just step four, which is the similarity search. So we then look for vectors in the database that are closest to the query embedding. So those are most semantically relevant pieces of context. Sorry, one sec. So step 5 is retrieving similar documents. So those retrieved documents is then combined with the original query to form a single augmented prompt. So this prompt is then sent to the large language model for generation. Upon generation, the response is given to the user. So that's about traditional RAG. Now, when we say agentic RAG, we are really talking about giving our systems the ability to think before it answers. One of the most common frameworks for this is called as REACT, which stands for Reason Act. So the core idea is simple. Instead of generating a single answer, the model goes through a loop of reasoning, acting, and observing what happens. If you look at the diagram, the agent starts with a thought. So this is the model's reasoning about what to do next. Then it takes an action, maybe retrieving new information, calling an API, or be it using a tool. After that, it gets an observation, meaning the result of that action, like the data it fetched or an error message, it's then observed by the agent. So this reasoning loop is what makes an agent agentic. It doesn't just retrieve or respond, it reflects on its own intermediate steps and adapts on its next actions dynamically. Now that we understand how agents think, let's break down what they are made up of. So there are 4 components of an AI agent. First, the LLM. This is the brain. It uses LLM like Anthropic or OpenAI's GPT models and all that. So it uses this LLM for reasoning, planning, and generating response. In an agent, it has a role and a task. For example, you are a compliance assistant or you're a troubleshooting bot for the product alpha that we just discussed. So the role defines how it reasons. Second, the memory. Agents has short-term memory, what happens in the current situation, and then it has a long-term memory, which helps it remember past context or user preference or previous outcomes. Third comes the orchestration. So this is like the agent's executive functions, the logic that decides to do what to do next. So it can reflect, meaning it can evaluate its own reasoning, query routing, or task planning, right? And then finally we have tools. So these are like agents and the external capabilities it can call. Tool can be as simple as a calculator or as powerful as a document retriever from the knowledge base or a web search API, etc. You can have multiple tools. So together, these 4, the LLM, memory, orchestration, and tools make up the functional core of any agentic system. So we talked about agents, reasoning loops, and orchestration. Let's bring it all together. What is agentic RAG system looks like in motion? So everything starts with a query. The agent first rewrites the query, clarifying ambiguity or be it expanding or adding missing context to your own query itself. That becomes an updated query. Then the agent itself asks, do I need more constant context to answer this query? If yes, then it dynamically retrieves information from external sources like the vector database or tools or even the internet. The retrieved context is merged with the updated query to form a grounded prompt and it's passed to the LLM. The LLM then generates a candidate response, but unlike traditional RAG, it just doesn't stop there. The agent now asks if my answers are accurate and well grounded. And if the answer is yes, if it thinks the answer is confident enough, it returns the final validated response to the user. But if not, the agent loops back. Maybe it needs to requery the vector store or maybe call a different tool or refine its reasoning until it's confident on the output. If actually not, the agent proceeds to the LLM with the query as is, then process the response which is generated. So this loop of like plan, retrieve, reason, validate, refine is what agentic RAG and its power. It's not just a pipeline, but it's an adaptive feedback system that reasons towards the best grounded answer. So now that we have seen the reasoning flow, let's go one step deeper into the actual architecture of an agentic RAG system. So I consider it as 2 main layers, a knowledge-based layer and an agent layer. Inside knowledge base layer, we have data source layer, the place where you actually store documents, and then you have an embedding layer where you convert the documents to numeric vectors. Then you pre-process it, which is parsing and chunking. I'll explain you this in the later slides. Finally, you will have vector store, like the embedding vectors will be stored inside this vector store. Inside the agent layer, we have the foundation model like GPT or Anthropic's Claude, etc., or DeepSeek, whatever, right? Which is gonna be the core reasoning engine. So then we have tools which are knowledge bases or external APIs and functions. Then we have orchestrations, prompts, tracing. Uh, Finally, we have instructions, task-specific guidance. I'll explain all of these layers in detail later. So there are actually a lot of great frameworks and platforms today for building agentic systems. Things like LangGraph or QAI or Microsoft Strands Agent by AWS or cloud offerings from AWS Bedrock or Google Cloud Vertex AI. For my prototype, I have chosen AWS Bedrock, and there are two key reasons why. First, Bedrock offers a fully managed foundation for building secure, scalable agentic systems. So second, it gives us a seamless integration on the AWS ecosystem itself, like the native access to S3 or vector stores like OpenSearch for tooling, storage, retrieval. All of that happens inside a governed AWS environment, so you don't have to go anywhere outside to build your logical layers. If it doesn't make sense on these services, don't bother. I'll cover it up in the upcoming slides. So what is Amazon Bedrock? So in brief, it's service offered by AWS. It's a managed service. It lets you build, customize, deploy generative AI applications using foundation models like via API. You don't have to worry about the managing the infrastructure. Bedrock also brings production grade capabilities. In terms of security and compliance, we have VPC integration, which lets you run Bedrock completely inside private networks, and we have your data encrypted in REST and a transit, so your data never leaves your AWS account. Second, in terms of scalability and reliability, auto scaling infrastructure handles traffic spikes automatically. And then we have multi-region availability, which ensures resilience and low latency access. Last is the observability. So Bedrock gives you a built-in trace visualization for agent orchestration. So you can literally see the reasoning and tool use steps. And also you get CloudWatch metrics for token usage, latency, and error rates. This is my point of view on building agentic RAG with Bedrock. So the first step in building an agentic RAG system on Bedrock is configuring the knowledge base. That's everything below the agent layer. First one is the data source. So this is where your documents actually come from. Bedrock can directly connect to S3. So S3 is basically a service offered by AWS to store documents on cloud like iCloud or Google Storage, right? It's of that sort. And then you can crawl websites or integrate enterprise systems like Confluence, Salesforce, and SharePoint. You can even plug in a custom connector for internal repositories. Second is the pre-processing. Next, this is where the parsing and chunking comes in, where we prepare raw data for retrieval. Parsing strategy. So consider it like how the information is extracted from your documents itself. In Bedrock, we have two options for parsing. First one is the default Bedrock parser, which is great for just plain text or simple PDF. Second, we have foundation model as a parser. It's better when documents include images or complex diagrams or any rich text format, right? Which will need model-based interpretation. So this is on parsing. Next, we have chunking strategy. So this strategy is like how documents are split into retrievable pieces. Based on your document structure, you can choose any of the strategy. We have like 4 or 5 strategies out there. Default chunking, I'll give you a walkthrough on one-liner walkthrough on all these strategies. So default chunking is by default given by Bedrock. It manages splits on its own. Then we have fixed size chunking. We have the texts are broken in token or character count for consistent windowing. And then we will have hierarchical chunking, which splits by headings or sections. Consider like a book content. Then we have semantic chunking. It uses embeddings to group conceptually related text. And then you have no chunking. If your document is already structured, treats each document as a single unit, rare for small files. Then we have the data processing and storage. So after selecting the processing techniques, you get to choose the embedding model and the vector store. In Bedrock, you get 2 model choices, Amazon and Cohere models for vector embedding with dimensions 256 up to 2024. And you can store either in floating point or binary vectors depending on your performance versus cost trade-off. And then you have vector store options where you have to store these embeddings too. You have OpenSearch serverless, which will scale on its own as traffic spikes in. And then you have Aurora's PostgreSQL, and then you have external stores like Pinecone or Redis Enterprise Cloud. So together, these components form your knowledge base layer. The foundation, your agentic RAG will reason. And also, I would like to highlight that this architecture remains same for traditional RAG as well. So once the knowledge base is ready, the next step is setting up the agent itself, the reasoning layer that brings your RAG system to life. So here's what process looks like inside AWS Bedrock. You start off with agent details, the basics like the name and the description, and then you move to the foundation model. You select a foundation model, and when I mean foundation model, it's like GPT-4o or Claude, anything of that sort, which is going to be your agent's brain. So the model handles reasoning, planning, and then generate logics that powers your agent. This model will be used across all of the items. And then moving on, we have instructions for the agent. So you set instructions. So these are system prompts or behavioral constraints. Think of them as agent's rule book, like how to respond, how formal the tone has to be, or when to differ, or when to refer to tools and all that. Fourth, you have user input. You can choose whether the agent should ask clarification questions. If this is enabled, the agent will pause, ask for missing context, and then reason better before answering. Then we have action groups. So action groups are nothing but tools, which, for example, we all know that LLMs don't have access to real-time data, right? If you ask for today's date or weather, they can't respond natively. With Bedrock, you add a Lambda function, which could be a Python code snippet where you hit or use a zone info library to hit and get the actual date and time here. Then we have agent memory. This keeps context across interactions, so your agent can remember previous steps, user preference, or partial results. And then we have the knowledge base. You can sync up to 5 different knowledge bases in AWS Bedrock. And then you have guardrails. Guardrails are nothing but safety nets. It's like redacting safety or sensitive information, like the topic filtering. Bedrock by default has their set of guardrails. You can add your own guardrails to it. Then we have the orchestration strategy. So this defines how this defines how your agent handles the reasoning loop, how it pre-processes the input, how how to coordinate across the tools, or how to post process. And then we have option to collaborate across multiple agents. For example, a policy agent might want to route a security related question to a security agent. So that's how you scale reasoning across multiple specialized agents. So in short, within a few configuration steps, you have gone from a static chatbot to a fully agentic reasoning system. This is a recorded demo, enough of slides. So far we have talked about what an agent is, how to configure it. Let's make it real. In this recorded demo, you'll see two flows side by side. So one is traditional RAG pipeline and the other is agentic. So how the second one doesn't just retrieve, but actually reasons about what to do next. We'll be digging into the trace to understand the difference, where traditional RAG fails, then how the agent actually thinks, plans, and retrieves. I'll pause and forward the video and explain here and there. I'll zoom in a bit. So I've actually created the knowledge base on the agent. I know everyone might have an itch on how to create this step by step. I'm pretty sure there will be YouTube videos or blogs to set this step by step. Considering the time constraint, I've already created it. As you can see, we have the data source here, and then we have the embedding model, and I've chosen Cohere's embedding multilingual model. And then the dimensions are 1024 with float vector embeddings. And then I've chosen open source serverless for vector store. So coming to the agent, you get to declare the agent name and the description as I discussed in the previous slide, right? Finally, you have an option to select the model. You have different options on selecting the model across different providers. And then you have instructions to the agent. So based on these instructions, your model is going to respond or reason everything. Then you have the action groups. Action groups, as I told, it's just a tool. So here I've created a tool already just to get the date and time out of it. And then you have the memory. Sorry, one second. And then you have the memory. If you want to retain conversational context across the agent, you have to enable that. And then I have synced the knowledge base that I've already created here. And then the guardrails I've left it with Bedrock's default guardrails. And then the orchestration strategy. So I've actually overridden few of the orchestration parameters like top P, temperature, or top K, just to show how the agent basically thinks. So I'm going to test the knowledge base with the same LLM model that I have chosen for the agentic RAG system. So this will act like a traditional RAG system where one second. So where you query and then you get answers for traditional RAG. I'll quickly show you the documents and then we'll dive into understanding the question answering. So these are all AI generated documents. As you can see, there is an effective date printed out there. The simple demo is going to be evolved around the effective date there. So the first question goes as, I'm new to the company and tell me about my leave policy. So as you can see, there are several source chunks which is fetched from the knowledge base. All of these source chunks are actually given to the prompt to the LLM, which will compare the query. It will then generate an answer which is more relative. And then the second question is, all about how many days back did the leave policy got updated. So as you can see, you have gotten a reply. 1 second, I'll just zoom in. As you can see, the leaves policy's effective date is being fetched, but my question is all about how many days back. 1 second, sorry. But my question was all about how many days back. It has to get the duration like from today's date. So this is where actually traditional RAG fails. Let us jump to testing the agentic RAG system. I'm going to ask the same two questions to the agent. Upon asking the first question, as you can see on the right, it is starting to think. It is making iterative steps or it is reasoning on its own. And then it is trying to the answer. As you can see, given the instructions, I have given the agent instructed to give in a markdown format, and we have seen the answer being generated in markdown format. And the second question is all about the same, which is how many days back did the leave policy got updated. And as you can see, it is giving us the duration 16 years and 21 days old from today's date, October 23. So the agent was intelligent enough to hit the action group tool to get the current time, and it's hard for you to like visualize the thinking in that. 1 second. So it's hard for you to visualize the agent's thinking process in the trace. So I've actually created a local code snippet Python which has some helper functions which is going to decipher the trace, and then it will print out how the agent basically thinks and all that. I'm going to ask the same two questions. As you can see, I'll pause it. As you can see, my query was, I'm new to the company. I'd like to know more about company's leave and holidays. But the agent is starting to think. It rephrased the query. Let me search the knowledge base for information about company leaves and holidays policies. And then it did the knowledge base tool. And it is invoking the knowledge base with company leave policy holidays, vacation time off with that query. And then we are actually getting answers out of it. And then finally, it is trying to think if the answer is enough. It is trying to get information about public holidays again with invoking knowledge base. Upon getting all this, it is given us the final answers in markdown format. Now let's run the second question. How many days back did the leave policy got updated? So first, it is invoking the leave policy. It is getting the necessary information, which is the date here, October 2, 2009. And then it has to know the current date. So it is invoking the action group, calculating the difference. So now I can calculate the time difference between the effective date and current date, and we can see it is 16 years ago. So this is all about how agentic RAG works in the background, right? So coming to key takeaways, RAG makes LLMs grounded. RAG anchors models in your organization knowledge. It reduces hallucinations and it improves accuracy. And then agentic RAG makes them smart. So adding reasoning or autonomy transforms static retrieval into adaptive multi-step problem solving. So cloud enables production scale. So platforms like AWS, Bedrock, and others make these systems deployable, secure, And then you get production ready without even heavy infrastructure complexity. So the future of enterprise AI is not just retrieval, it's a reasoning autonomy. Agentic RAG systems are a powerful step towards that vision, according to me. So I just want to finish it off with like, imagine your next search bot not just answering, but thinking before it answers. Thank you for allowing me to share these learnings. I'd like to give reference to VV8 and then Daily Dose for helping me build this deck. Any questions? Are there any? Okay. You can actually post your questions in the chat Q&A, or you can unmute. You can even raise your hand and the team will be able to unmute and we can just clarify it. Is it? Nandini is raising the question on.
Hi,
Nandini, you are on
everybody.
mute. You can actually ask the question.
Hope my voice is audible, right?
One second, just it's feeble.
Okay. So, hi, everybody. This is Nandini. So, thanks, Aris, for this wonderful session about the RAG and the agentic RAG. So, here my question. So, I also be working with some of the agentic related RAG. So here my question is like, I have like a knowledge base, which is more like different versions of knowledge base. Like, I have a company documentations, and along with that, I have um, documentations. Along with that, I have like a few things which I have Zendesk resolver tickets, or I have like a more vast amount of knowledge base. I just want to know like how we can manage this, different varieties of knowledge base into one particular agentic rack, because I actually building a agentic rack, but I finding like one of the pain point is it's not able to retrieve like what particular document that customer is actually looking for. Instead of it's just get for that based on that similarity ranking. So I just want to make sure that what that people is actually looking for, we just have to fish particularly from that particular knowledge base instead of making it like similarity matches. So how we can do that?
So understood, right? So to answer this, it's more of like how efficient or how we can basically structure the embeddings or how we can store inside vector stores. You can have different data sources created for instance, like you said you have vast different sources of documents, right? So you can have multiple data sources and then you can create a knowledge base out of it. To gain more accuracy, you need to focus more on. Okay, so to gain more accurate answers, you need to focus more on how to create a vector database or how the embedding has to be. So to give you an overview, the last session is all about how you can get the best answers out of it. So you will have to wait until the last session to get the best out of it. But then you can have multiple data sources as we discussed inside the knowledge base layer. You can then integrate. So yeah, actually, and the parsing and chunking strategy that I discussed can actually help. So I discussed about.
Yeah, now I'm currently using like a fixed chunking.
Fixed chunking is not great when you have vast information. So if your data is structured in a more meaningful way, then you prefer semantic chunking. And I personally have built the system with semantic chunking and it has helped it. You can actually select the chunking size also. So there are researchers who has helped us understand what chunking size you basically need to choose for your data. So you can dig through on what chunking size needs to be chosen or what chunking strategy and all of that. And if your documents contain a rich format like images, which most of the RAG might fail in getting proper answers. Initially, we faced that problem. So you can use a foundation model to basically parse those documents because you need a parser to basically scan the entire document and fetch the information out of it. So you will have to focus on parsing and chunking strategy. And of course, the last session is about vector database, which is the core brain. Yeah, so hope I answered the question. If not, you can ping me on LinkedIn or wherever I could help you with it.
Yeah, thanks, Harish. Thanks for the response.
Yeah. Let me hand it over to Abrit. So he is my partner in crime. We graduated from the same college and joined TCN together. Ended up being in the same team for like 3 years. So we started off doing ML research on textless NLP speech models, and then we built the agentic RAG system that we talked about together. So he's an engineer on the frontier AI research, ML or cloud deployment. Let me hand it over to him to talk about agentic RAG and edge applications. Thank you. Thank you.
Thanks, SRIHARI. Thanks for a nice overview of Agentic RAG on cloud. Hi, everyone. I'm Abrit. I work as Associate MLE at TCIN, and I've been working here on textless NLP, speech technology, large action models, and Agentic RAG for quite a while. And I'm going to share my experiences with you in this talk. So as SRIHARI mentioned, I'm going to go through this area of RAG where it is less talked about these days, but it is getting traction and people want to explore this more. And I'll share my experiences and some learnings that I went through as I was researching for this and working on my passion projects also. So let's see the roadmap of this talk. I've divided the talk in 4 sections. Why we need edge RAG, first of all. We have a large infrastructure of cloud where we can host models, create complex agents doing which can do complex reasoning, but still there's this thing called edge RAG that we need, and sometimes it becomes a necessity depending upon the problem and certain depending on the problem. So I have a question for all of you. Have you ever felt that you need an AI agent that solely works on your personal device? Have you ever felt that in some recent time? To be honest, I never felt that, but recently, last week, this happened. So jokes aside, I'll honestly talk about why we need edge RAG. So edge RAG presents lots of possibilities for us to explore. First of all, bringing down our RAG systems to devices, our local devices means there is less cloud transmission, which brings down the cost a lot. Since there are a lot of compliances in certain areas like healthcare that you have to comply with, sometimes having the whole data and the agent itself inside the edge system gives an edge and makes the whole project compliance friendly. Even edge RAG presents us with a zero trust model where the data remains with the person who owns the data, and as minimal amount of data is leaving from the edge device, people can be at ease about their data. Another thing that I mentioned earlier also, it's offline capabilities. This is something I want to talk about because it's harder to have complex RAS systems completely offline, but there are situations where this can come to handy and be useful. I'll show you a demo on Edge RAG. These are two agentic demos where I have implemented an Edge RAG system to carry out some tasks like sending an email, sifting through Google Maps to check a location, or changing some system settings. This is very similar to what you see in browsers like Atlas or Comet. But this is a POC and focused on simpler tasks. And this whole thing implements RAG for the implementation of RAG brings in memory into it, which makes the inference faster and less dependent on the agent or LLM itself. I'll run the demos. The first demo is where I'm giving a NLP query to search for IIT Madras on Google Maps, which the agent runs through the memory RAG and checks if a similar memory was run earlier, checks if the vector database contains it. Yeah, there is a match, and then it will carry out the process. It is very similar to automation that we do in other applications, but here we don't define the automation. We just give an NLP query, which is being carried out through this agentic system where the LLM and vector database work together. See, it was able to search for IIT Madras. Similarly, the other demo talks turns on the Bluetooth in the system settings. Similar way, I asked it to turn on the Bluetooth. It will go into settings. First of all, it will look for the memory. Yeah. Yeah. And carry out the automation. Now that we understood why we need RAG, basically the cost benefit, data privacy, being focused on privacy really, and efficiency when it comes to energy consumption also, as these LLMs, the foundational models, require a lot of energy when they run. Now we'll understand the basics, and now we'll understand what Edge RAG means and how it is different from your cloud-based RAG. Basically, there are two kinds of approach that we can see: a local on-device RAG and a hybrid RAG. Local RAG means you have all the components inside your edge device, which can be anything from a phone, a refrigerator, an IoT device, your car, anything. And hybrid device is where we rely on cloud components where the task is difficult to be handled on the edge device itself. I'll go to the next slide. Yeah. So these are the components that we saw previously in SRIHARI's talk also. Some of the similar components which are found both in Edge RAG and Cloud RAG are language model, agentic layer, then context memory, vector store. But there are certain things that we sometimes need to give more attention to. For example, runtime optimization, as it can be difficult to run the LLM, the inferencing on edge devices, and it requires a lot of processing power. Having context memory also helps and saves time and compute itself. Then, since there are multiple apps, multiple functionalities in an edge device, you might need a tool calling system which can orchestrate through different apps and applications. Yeah, next. I'll go through a very simplified flow for an agentic RAG application where a person writes an NLP query, a natural language query, which is then embedded into embeddings and then stored in the DB. What happens then is the agent gets these embeddings and uh, makes the tool call or tries to generate a response. If this particular task requires multi-stage reasoning, then we might have to we may see a tool call being returned to the agent. So when all the tool calls are done, this output is returned to a LLM to generate a final response, and you also see local memory at the end, which is your cache. Now we understood the basics, why we need RAG, understanding the fundamental components, which are very similar to cloud, but with certain differences and quirks, to be honest, being low compute being an issue. Let's see how we can build RAG. There are certain tools, resources online that you can go through and build your own app, a POC or a passion project. I'll talk about some of the tools that I have used earlier. For backend layer, there's a framework by Google called Media Pipeline, which helps inferencing LLM models on an edge device. Then Edge Portal is also by Google, which is a platform for testing for different kinds of device architectures. Light RT or TF Lite community is a community or inferencing engine where you can design LLMs for edge, which aren't resource intensive. Then another resource is IRE Dev, which is an end-to-end solution, open source solution, which if you don't want to opt for the other tools, you can go with this also. Then this is a very important question before you start building RAG. There are certain scenarios where an edge RAG system will suit. Sometimes you might have to go with fully on-device RAG, hybrid RAG, cloud RAG. Sometimes an agent is not even needed. See, for example, if the privacy is the first point of concern and the KB is small, you can go build an on-device RAG. Privacy is a concern, but there's a large DB, you might have to opt for hybrid. For complex situations, you will go for a complex, for a cloud agent. And in the same way, for simple solutions where offline, where the data being offline and cost being reduced is the main point, you can go with a standard RAG. We need to see that, we need to understand this one thing, that even though we have all these resources available to run agentic systems on edge devices, they are still low on compute, low on device memory, and it is difficult to run complex agentic systems. So if your utmost preference is quality and speed, kindly choose Cloud RAG. Now we saw why we need RAG. We understood how RAG works. We went through the tools to build RAG, but when it comes to edge devices, it's very important that you optimize your system, be it memory, compute, retrieval, the LLM itself, so that it can work over a range of devices which may not have as much resources as a cloud system. There are multiple optimizing strategies, if not hundreds, then tens. But I have chosen these four, and I'll talk through each one of them one by one and explain how these can be useful while implementing or optimizing your edge RAG systems. First of all, SLMs. We have come across a long way from GPT-3 to 4 to 5, and now there are smaller LLMs which, when fine-tuned, can be on par with LLMs like a full-fledged LLM which have trillions of parameters. Then we look at different retrieval approaches so that it is easier to retrieve embeddings or vector embeddings from the data store on low compute devices. We'll also see, I went through this project where they suggest to have on-demand embeddings while fetching or indexing uh, for vector from the vector store, and especially pruning your embeddings based on the load heaviness of the embeddings. I'll talk about it in next few slides. Then the last point, optimizing for inference. Sometimes running through the whole process of reasoning may not, or running through LLM might not be needed, because you might have ran the same query again and again, and the whole computation is not needed. So optimizing strategy number 1. First one is the SLMs. So as I talked, SLMs have this ability to be a master of none, or be specialist about one thing and keep doing that thing so perfectly that they are comparable to very large LLMs. But there are certain pros and cons of SLM that I want to point out. First being the cost. Uh, being able to run SLMs on edge devices make them very cheap. You just have to purchase the device once and you can run them again and again. But you still have to pay the baseline price of a foundational LLM that you hit on the cloud. Fine tuning in SLM is relatively easier, takes less compute, takes less time, and less painful. When we talk about different kind of tasks, and most of the time what happens is we are building agents to perform simpler tasks, and the same kind of tasks are being repeated again and again. So in such situations, we don't need bigger, larger LLMs which have ability to do all kinds of tasks. We can focus on certain kind of area and implement with an SLM. There is this thing about LLMs that is being talked about is when we tend to use an LLM in a project, most of the time, since it's performing similar kind of tasks, but its ability, foundationally it has trillions of parameters, but still only few number of parameters are being used, since the task is being repeated or it lies in the same area. So it makes better sense to fine tune some kind of SLM with certain kind of data to make full use of that SLM, and don't go overkill for the compute or the large language model itself. The last thing is, as I earlier said, it's good to use them in repetitive tasks, but when the tasks are open domain and complex reasoning, you might have to go with the larger LLMs. Now, what I have here is an example of a small SLM, which is 2 billion parameters in size, and I'll explain how powerful this SLM can be. The base model of this SLM is this small VLM v2, and this has been fine-tuned in 2 stages on this AGU via stage data. No, so what happens here is, now this data contains different episodes of tasks. For example, sending a mail, changing some kind of setting, the tasks similar to what I showed in my demo. And here is the prompt that I fed to the SLM, which is, please generate an email which sends greetings to this person. And one by one, I passed the screenshots to the SLM. The SLM was able to generate all these responses without any external data help, which shows how capable these things can be. You can do similar thing when you use basically Claude or GPT-5, but that is quite overkill in my opinion. Now, optimizing strategy 2. We looked at SLMs. Now we'll see how we can make our retrieval easy. So what happens in a normal retrieval system is you take the entity, you chunk it into different nodes, and you try to semantically match different nodes in that vector space. But what is suggested is the lightweight graph-based knowledge retrieval system, where the nodes are divided into two things: the uh, identity type answer and the uh, step, or what I would call is key pairs. The answer type, as in if a quick query has been asked, what kind of answer it would be? Is it some kind of a social interaction? Is it some kind of a location? Are they talking about some event? And the other segregation is what relative key value pairs are there. So what happens here is, since you define them in two different sections, you first try to look for the type of answer which is which has a subsection called key pairware, and this makes the graph traversal to find the particular answer easier and less heavy on compute. This particular approach makes the retrieval of the answer almost 25% faster, or I would say less heavier on the hardware. We'll go to the next optimizing technique, which is on-demand embedding. So in general, what happens inside an embedding system is you have a query, you embed it, you index, and you create nodes out of it, which later generates response. But what we'll do is we'll categorize our embeddings in three sections: first level index, second level index, and cache. First level index, here in query embedding, in step 1 and step 2, what we are trying to find is the centroids of the cluster, which is what happens inside a vector space. Is you divide the whole vector space into different clusters and try to find similarity between the nodes present inside. So what you do is you try to find the first centroid. Then in second level compute, you keep the embeddings which are heavy, computationally heavy, cost heavy, and the embedding cache you only keep which are lighter, easier to embed on the go. So what happens here is you look for the heavier embeddings in this, and if the relative embedding which are lighter in nature are not retrieved, are not present in second level embedding, you generate them on the go. So what makes this whole system helps us save a lot of storage, and even makes the retrieval faster. Not faster, but I would say efficient. Now, last point for optimizing. This is something that many people would be familiar with, which is key value caching. It is very similar to last two approaches, but follows a different route. So in an attention model, what we have is a key value embedding. And when a question is asked, we embed these two things one by one. But in each step, in autoregressive embedding, what happens is whenever a question is asked, you generate these embeddings again and again. But this approach, what it says is you save these key value pairs in cache, and whenever there is inference being done, you try to fetch these values from the cache itself, and which makes the whole process of inferencing easier, compute heavy, less compute heavy, and faster. Yeah. Now we'll wrap up and go through our whole PPT and see. We learned why we needed RAG. We understood how it is different from cloud RAG. We saw the tools which can help us build projects and agents, on-device agents, basically. And then we looked how important it could be to optimize these rack systems. I'll end this with this slide, which is one of the most important slides when I would suggest somebody making edge rack systems is to keep these things in mind. First of all, understand what the problem is and what kind of optimization technique or I would say tool you require to build your project. SLMs save on cost, but have a minimal accuracy drop. Similarly, you can use techniques to use lower compute retrieval, same way on-demand embedding as I talked about earlier. KV caching was also another thing which can be which free up a lot of memory, but when the context becomes very large, can be heavier on the GPU. The last point, which is the main one, I would say, is we need to understand that edge has limits and it can only perform certain kind of tasks. We need to stay away from complex reasoning tasks and break our problem into smaller agents or smaller uh, uh, projects which can be handled or handled through these low compute devices. Thank you. These were the references I used while creating this PPT. Does anyone have any questions? You can paste the questions in Q&A section, or you can ask them live. If you want to, you can also connect with me on my LinkedIn or Twitter. I'm Abrit Pal in both places. Should I move? Now, I'll introduce the next speaker. So, Sundar, the maestro at intersection. I'll give an introduction for Sundar, where Sundar is where LLMs, APIs, and VectorDB come together. He's making RAG smarter, cloud deployment less dramatic, and you'll mostly find him at 2 a.m. knee deep into Gen AI debugging Python, building Docker projects. Hi, Sundar.
Hey, thanks for the AI build-up, Abrit. So, hey everyone. Hi, this is Sundaresan. So from here on, I'll be taking up and I'll be talking about the heart of these RAG systems, vector database. So the session title is designing and building the right vector database for your RAG system. So let me start with a question. What is the hidden brain behind RAG? So already you guys must have seen how RAG works, right? It's the neat moment when an LLM does a quick phone a friend before replying to you. In that way, it gets the relevant context and gives you a response. And what is the system that gives you the relevant context? It's a vector DB, very simple. And what is the fuss about? I mean, bro, we have better things to talk about like LLMs or RAGs, but why this? If you are such a person, this PPT is for you because your RAG system is only as smart as what your vector DB retrieves. Okay, so say if your retrieval layer is giving you irrelevant chunks, then even GPT-5 can very convincingly give you a response on how moon is made up of, say, paneer. So you don't want that, right? So then you better learn how vector database works in order to understand how to choose it, configure it, and build it for your use case. Um, so let's move to the table of contents. I will be beginning from foundation of vector search, right from scratch, how vector embedding works, um, distance metrics, and vector search, ANN, KNN, everything. Then once you know what a vector search is, I'll be talking about how to fasten this via ANN algorithms and indexing techniques, how to make it optimize. And once you have these algorithms, they need some system to run. So that's where database architecture and scalability comes in. And with scalability comes the problem in terms of memory storage and persistence. So that's where storage, memory, and some advanced search techniques like hybrid search comes in. And finally, we'll be ending with performance, optimization, and ecosystem because you want your system to perform better. So foundations, let me start with vector embedding. So say, for example, your data can be of text, image, audio, or video. It can be anything, but you need your machines to understand. That means machines only understand numbers. So we need some translator, and that translator is a vectorizing model, which is going to give you a array of real numbers. And this is what we call vector embedding. And each of these real numbers, or what we call as dimension, so the total length of array is that much dimension of that vector embedding. And by proper definition, this is a representation in n-dimensional space where each of your dimension is going to capture certain feature or characteristics. Say, for example, here the 0.67, as in the vector embedding here could represent, say, cat, where 0.67 could represent its eye, 2.45 could represent its claw, things like that, just for an example. On a different analogy, I can visualize vector embedding more like a barcode. So say, for example, you have each of your numbers, you can think it more like the stripes in the barcode. So the bigger your number, more darker it is. Lesser your number, more whiter it is. And if I take, say, two barcodes, one represents cats and one represents, say, hamburger. So these are going to light at totally different regions. But if I take two barcodes with cats and dogs, they are going to similarly light up in the same regions because they talk about the same sentence. So this is how we are able to find the semantic similarity via vector embedding. So before talking about vector search, you should know how this search got evolved over the years. Starting with keyword search. So this is a lexical vector, meaning you are representing a word only based on its frequency. And the representation is very sparse. It's like 10010. So this is how it started. Then it went to neural sparse search, where that's where the transformers came in. And we started our model to make it enrich the queries and documents with token level signals. Still sparse, but it is somewhat aware of the linguistic context. And then comes neural dense search. So this is a proper dense semantic vector, a continuous embedding. So this is where both your queries and documents can through which we can actually understand the semantic similarity rather than just exact keywords. So this is not a simple context aware, but it actually understands the meaning. So for a simple example, I can say, for example, you're asking a question like, do I want to take a break? I mean, how do I take a break for a day? To my policy pal. So policy pal is just an office chatbot. If you use keyword search, it will search for the documents. Okay, what to do with broken laptops from IT documents. But if you are actually using a neural dense search, it will understand that break actually means, okay, he's asking for a leave. So it might actually get the right documents in that case. But again, sometimes hybrid works even better, which we will see in later slides. So how a vector search works? So say, for example, you have some 1,000 internal policy documents. You want to make this searchable. The first step is you are going to feed this into embedding model, which can be OpenAI or Cohere or Hugging Face. We get vector embeddings. For simplicity, I'm representing it in the 2D space, project them, but in reality, it's an N space. So then a user query comes in, say how many leaves do I have? And this is essentially an LO point. Now my goal is to find similar documents for this. So how do I do it? So this is where distance metrics comes in. So basically what I'm trying to say is by similar documents means you're finding the nearest neighbors for that query data point. And in order to find that, you're using these distance metrics like cosine or Euclidean metrics, which you might have already know about. And to make it easier, this is where this algorithm comes in, which is called k nearest neighbor. So it's going to find the k most similar data points to a given query based on only distance in the vector space. But you're going to do an exhaustive search. And of course, the recall is going to be 100% because you're literally comparing your query point against every other data nodes. But on the downside, this is a brute force. So it's literally O of n times d, which is very slow and computationally expensive for large data sets. So what if I come up with, say, an approximate neighborhood and then do an exhaustive search within this neighborhood rather than doing an exhaustive search? So this is where ANN comes in. So this is basically a data structure for efficiently finding your nearby vectors. Okay. I hope you guys were hearing all this file. But okay. This is a data structure for efficiently finding nearby vectors in high dimensional space without doing an exhaustive search, and for which we can use graph or hashes or trees. And the runtime of this will be logarithmic time, log n times d. And this is very faster compared to your normal brute force technique. And recall wise, it's also high, 95 to 99%, but still there's a slight loss in accuracy because you might miss out some points when you draw the circle, but which is fine. For a trade-off of massive gain in efficiency and scalability, then yes, I would go for this. So now that you have learned what is an ANN, let's take some popular algorithms in ANN. Let me start with, I think, some people might have already known about this, hierarchical navigable small world, HNSW. So this is inspired from two data structures. One is a skip list. So, okay, imagine, say you have a sorted linked list and you need to, hop to a target node. So how do you do it? You start from one, say here, the target is 19. So you start from 1, 5, 7, 12, 15, then you go to 19. But instead, what if I add some express lanes? So some shortcuts to skip over multiple nodes. So that's what skip list does. So it's nothing but it's stack of multiple linked list on top of each other. So your bottom layer is going to have all your nodes. It's basically a sort of linked list. But as you go top, only a random subset of these nodes are going to get promoted. So in that way, say for example here, you will start the topmost lane, which I call it as fast lane, and then you move forward quickly until you encounter a number which is greater than target. So then you find a local minima there, drop down one level, again do the same greedy search, and go to in that way. So in this case, you hardly did 5 to down 5 to 15 to down 15 to 19. So it's just 3 hops instead of doing 6 hops. So this is very fast and logarithmic times runtime. And coming to navigable small world, this is a simple graph where nodes aren't directly connected. Most of the nodes, I mean, only few nodes are connected with each other. So what I mean is it will have high clustering and a shorter average path length between them. So in that way, if you're going to navigate in this graph, you only have local information. You don't have a global graph information, but only within few hops, you'll be able to hop to your target node. So that's what is this about. Okay, now let's go to the actual HNSW implementation. Just a quick glance. Okay, see, this is a proximity graph where you can think of it like stack of graphs. Your top layers are tiny and gives you long range jumps, shortcuts, just like how we saw in the skip list. And the bottom layers will be more denser, and that gives you fine grained neighbors. Okay, let me demonstrate this. Say, for example, you are getting a new document, and your task is to insert this document in this graph. So how do you do that? So let's start with, say, okay, I'm going to assign this document with some number of layers using a exponential distribution. So this exponential distribution will make sure only very few nodes gets promoted to the top of your layers, but most of your nodes will be at your bottommost layer. So in this case, it has been assigned with 0 and 1. And let us start from the top of the current graph. So this is essentially your starting node. And please don't mind that new document node. It's not present there. We don't know where it is present. We are supposed to place it there. So that distance is not the distance. We just know the coordinates. And we are going to find the distance between this starting node against your new document. And then I'm going to do a greedy search, like how we did in skip list or your NSW. So in this case, for example, its neighbor is not as near as this. So you go one layer down, again do a greedy search, find the local minima there, then go one layer down. Maybe here again, this is the local minima compared to its neighbors. So you like that, you go to the bottommost layer. So here is where things getting interesting. We are going to do something called a local beam search. So until now, if nothing is everything going over your mind, so I can come up with an analogy. What I'm trying to do here is, so this core search, you can imagine like, say you're randomly spawned in Tuticorin, and you're supposed to come to my house in Chennai. So what do? You have to first take highway lanes, Thoothukudi to Madurai to Trichy to Chennai. So now we have reached Chennai. Now you have to find my area, which is Gindi. Okay, now that you have find my area, you have to find my street, which is Ranganathan Street. Okay, until here it's fine. This is all just sparse neighborhood. It's not very crowded. You can just follow the signboards. You have come until here. Now we have reached the bottommost layer. So inside the street, you have to find my house. So this is what a local beam search is about. So what I'm going to do is I'm going to maintain 3 elements. One is called a priority queue. So one is called a visited set, and one is called a candidates list. This is a bit mathematical, but let me try to put it in simple words. So this candidates list will hold the nodes to explore potential candidates. And this visited set will make sure that you are not visiting again and again the same nodes. And the PQ list is what is your actual sorted list. So that is going to be your final list of nearest neighbors. So, and we can't keep doing this search, right? So we have to put some threshold during the iteration. So that is where this parameter called EF construction comes in. So and once you find, so you are going to do a search until your list either exhaust until EF construction, or you don't find any more neighbors more closer compared to your visited set. And once you're done with this, you have to just connect your top M nearest neighbor among this list. So say, for example, in this case, my EF construction is 4 and my M is 2. So among the 4 nodes, the top 4 nodes, I'm only taking the top 2 nodes to connect. And yes, optionally, this is also present in layer 1. So we should not forget that. So I'm going to do the same repetitive process to make sure that node gets inserted there as well. If you have understood indexing, search is very simple. The same process, you start from the top of the graph. So we will skip the number of layers because we are not going to insert it, but rather we are only interested in the number of neighbors. We will go one layer down, repeat the greedy search until your bottommost layer iteratively. And again, here we are again going to do a local beam search, but just with one difference. Instead of EF construction, the list will be stopped by EF search. So that is a third parameter. And among this, you're going to filter out your top k neighbors from the queue. So k is your fourth parameter. So yeah, these are the parameters we have discussed. I'm just displaying it here for a production level ideal numbers. You can refer this and sorry. So pros and cons. So pros or it is a logarithmic query time, which we have already discussed. And this is also involved with the high memory. Why high memory? Because we are not just storing the vector data points, but also we are storing its neighbors. So it is increasing by a factor of m. If you remember, m is the number of neighbors for your new vector coming in. So that is on the con side. And also this supports incremental insertions, which we saw. It's very dynamic. And you can also tune your recall latency. So for example, during search, if you're setting a very less EF search, so your search exploration will be stopped until there. So your results will be faster, but you're not really exploring more neighborhood. So you're coming to a conclusion very quickly. So your recall might fail. So this is the trade-off. If you want a better recall, you have to go for a higher EF search, but you have to wait. And yeah, no true deletions and slow index build are some of the cons. So coming to inverted file indexing, okay, let me directly demonstrate this. So say, for example, you have your documents. These are your black dots in a 2D graph. And I need to first index this. So what I'm doing is I'm going to cluster this via k-means clustering, partition this whole data set into n list clusters, where n list is a parameter. So n list cluster here, say I'm keeping it as 4, so 4 centroids. And then I'm going to assign or map each of these vectors to its nearest centroid. In that way, every cluster will be nothing but an inverted list, where your index will be centroid and your list will be the vectors in that cluster. And the name inverted list is inspired from inverted index from your keyword search, if any of you are already aware. So coming to querying, say if I introduce a user query, which is a red dot, now let me do a core search. So compute the query distance to all centroids from this point. So mind that I'm not doing an exhaustive search, but only comparing it against the centroids. So to understand which region this is more closer to. And among that, I'm not going to look at all the centroids. Say I'm choosing the top n probe, which is 2 in this case. So which is going to be the green and yellow clusters. So within these clusters, I will do a fine search, that is compare my query against all the vectors within these two clusters. And that is going to give you a final list. So you have to just rank it or sort it, then output the top k nearest results. And these are the parameters we have discussed. They are typical range in production level. And some pros and cons. So fast search via coarse clustering, which we saw just now because of centroids. One problem with this is that, again, this is approximation. So you will have a slight recall drop because you're essentially clustering them. You're not going for the exact vector search. But on the other side, this needs k-means training every time. So if you're having a use case where your data set grows, say, every then and while, this is not an optimal approach because you can't keep training your data set before your search querying. And also this is not ideal for frequent updates. That's what I said. And there is some memory overhead because of this inverted list we saw. But on the positive side, it can scale up to millions of vectors. If you have a very big database and say you hardly update it, this is the algorithm I will suggest. And also tunable recall speed, just like how we did in HNSW. And it works well with some of the hybrid algorithms. Like you can combine both HNSW plus IVF and along with PQ. So PQ is something we are going to discuss next. PQ is product quantization. So let's say I have a database, 50K vectors, each with 1024 dimension. This also sadly has a clustering part, so please bear me with that. So you're going to chop this data set into m subvectors along the dimension. So every subvector is going to have a dimension of, in this case, say if I'm dividing it by 8, so 1024 by 8 is 128. So on this, I'm going to do a k-means clustering over each of the subvector space. And the way I do is that if you're doing k-means clustering, you will know that you should set a k centroids. And this k, I'm going to set it as 2 power n bit, where n bit is another parameter. So in this case, for simplicity, let's fix n bit and m as equal, which is 8. So the number of centroids you're going to get is 2 power 8, which is 256. So each of your subvector space is essentially reduced to just 256 integer ID centroid space. And this trained centroid space is what we call as cookbook. And this is very important in the upcoming process. So, okay, how are we compressing now? Okay, so for a given vector, yes, you have split the vector into subvectors, and each of the subvector, I told you can represent them by its nearest centroid. And this centroid is a number from 0 to 255, so it's 8-bit. That means essentially a whole vector can be replaced by the centroids of each of its subvectors. So in this case, we are drastically reducing from a 4096 bytes to just 8 bytes. 8 times 8, 64 bits, so 8 bytes. So that's a lot, right? So it's literally 512 times memory compressed. And this is highly useful, say, if you're working in a workload where you have a constrained memory. And also one more thing we'll do before querying, I'm going to pre-compute all the possible pairwise distance between all the possible centroid IDs. Because you already know these centroid IDs, so just you're going to create a lookup table which will be useful for the querying part. So in querying, what we do is we'll calculate the approximate distance between your given query vector against the data point. Not exact vector to vector match, but it's going to be this compressed centroid vector against the compressed centroid vector. So that is interesting, right? And not just, it doesn't stop there. We already have a lookup table for this. So you don't even have to calculate the distance. You just have to see the table and fetch the value, put it against your dimension. So similarly, in this case, 8 dimensions. So you're going to take 8 elements from the table. So boom, you're reducing the complexity of calculating from O of dimension to O of subspace. So in this case, from 1024 dimensions to hardly 8. So that's a huge thing in terms of search querying. It's really fast. But yeah, it also comes with its cons, which we will discuss now. Again, these are the parameters which I've already discussed. And again, production level numbers. So pros and cons, yes, because of high compression, you have low memory and low compute. But on the con side, quantization will lower your accuracy. So you should keep that in mind. And a very fast distance computation and works well with IVF. And on the con side, again, this also requires separate training, just like how IVF does. So you have to keep that in mind, and less effective for a non-uniform data. Otherwise, you cannot cluster this. Same works for IVF. So keep that in mind. Oh, oops. Okay. This slide should have been my first slide, but okay. If anyone are already sleeping by my mathematics, this is the time you can wake up. What is a vector database? So, okay, if you listen until now, it's simple. It's executor of ANN algorithms. You choose HNSW, IVF or PQ, choose a embedding model, do a vector search, finish. Not quite. It has more to it. It has index management, it has persistence, hybrid search, load balancing, metadata filtering, monitoring, and APIs. If this is all gibberish, then you have to listen to the next set of category of my slides. So, okay, first okay, as I already discussed, we have seen how algorithms work, but we need a system for these algorithms to work. So this is where architecture and scalability comes in. Say, okay, everyone are aware that a vector can be stored in a single node or a distributed cluster. In a production level, distributed cluster is nothing but multiple machines instead of using a single machine. And this, though complex, this is highly scalable. So for a production environment, this is what we choose. And say you are distributing data set among these nodes. So for example, 3 machines is there. So this process of distributing the data set among different machines is what we call sharding. And each of the smaller subset is shards. And say, for example, if one of this machine fails, your shard goes with it. So it's a waste, right? To counter that, we add fault tolerance. So which means that you're just adding a copy of that shard in a different machine. So this is replication. And to orchestrate all this, you're going to use load balancer, which routes your query to the right shard or the right replica based on the load. And there are some guidelines, practical shard and replica guidelines. So if you're using too many shards per node, you will have a heavy coordination overhead because you're not computing within a single data set. Your data set is distributed. So you have to coordinate your shards for indexing or for searching. And too few shards per node, that will be underutilized resource. That will be a waste of resource. So you should find the sweet spot. And my recommendation is 10 to 50 GB per shard. So this is something I got from Elasticsearch practical usage and guidelines. And replicas, you can keep it 0. If you're in a dev environment, please don't waste your money. But if you're in a production, then yes, keep it 1. And gradually, I would say increase it because 1 is more than enough. Multi-tenancy. So yeah, this is where I think Nandini's topic comes in. So she asked me, she asked 3 questions that I have different categories of my data set. So how do I maintain this in a single collection? So this is where multi-tenancy comes in. So within the same index, you're going to partition your record into namespaces. So what happens is all your data operations are going to be targeted to that particular namespace. And inside that, we are going to do any search or upsertion or anything. And how will you predict that namespace? You can use Agentic RAG as an LLM based on the user query. And one more technique is elastic scaling. This is nothing but an auto scaling. So based on the load, it will either add or remove more compute nodes or your pods, which is like storage nodes. Okay, so let's move on to storage. What are the types of memory handling? So either you can work on a pure in-memory system. So this is what most of your ANN algorithms I have discussed works on, like HNSW. It's going to keep both its graph and vector entirely in RAM, which is super fast, by the way, but limited by its size, and it's an expensive scalability, right? So on the other hand, you can use a pure disk-based system. It's going to keep everything on the disk or SSD, which is, by the way, can handle massive data set, cost effective. But on the con side, each disk access time is very expensive. So you have to, if at all you're going to store your data set in a disk, you can't keep calling it, but you have to make some clever decisions in terms of those calls. So this is where let me introduce disk ANN. It's a hybrid novel approach. So disk ANN essentially what it does. So opposed to most of the ANN algorithms which focus on in-memory performance, this can enable efficient index storage on SSDs while maintaining competitive search performance in on memory. So more like a hybrid approach. Okay, what happens here is you have a data set. Okay, you can vectorize it, make it embeddings. So on this embeddings, we are going to do 2 processes. One process, let me cluster them. And among each of these cluster, I'll make a graph out of them via a different algorithm, not this HNSW. And then I will merge all these graphs into one graph, store them in SSD. So that is going to become your index graph. On the other hand, I'm going to compress these embeddings using PQ and store them in RAM. Since you're compressing it, you are allowed to store them in RAM. It's going to occupy a very small space of your RAM. So during a search time, what happens is, um, it is first going to do a core search among your compressed vectors, just to find where is a neighborhood. You're not going to fix your neighbors, but you're just trying to go near to the neighbor. And once you do that, now you have some potential candidates. These potential candidates, you can retrieve its full vectors from SSD. So in that way, you are only using a very small subset of vector dataset inside your RAM, but most of your dataset actually lies in SSD. So this is a state-of-the-art algorithm for a billion scale vector search. So from the data I have read, this can give you a recall of 95 to 97% recall for a billion scale vector, where to give such a recall against your other ANN algorithms, that will be around only million vectors, not billion vectors. So this is greater than whatever we have discussed. And why it is? Because it uses a very intelligent algorithm called Vamana algorithm. So in all our previous algorithms, say if one such is HNSW, most of your graph algorithms, they start from sparse to dense. They build from scratch. But here it starts from dense. So you randomly connect your end nodes. Then you do a pruning process to slowly cut off the unwanted edges. And at the final iteration, you make sure that each of your nodes are optimally hoppable. By which what I mean is both your local and long range connections are stable or optimal. They are not, um, you know, yeah, they are optimal. I don't want to dig deep into that. So this employs, so basically what this does is, this will give you a flat graph, unlike your HNSW hierarchical graph. So your exact location of each of your node's neighbors can be already predetermined. In that way, you are making your information retrieval faster and more efficient despite your slower nature of disk storage. So this is why in SSD, it won't make multiple calls, but make clever calls. Okay, so let me start with actual architecture. So Milvus, this is a great example. This is open source and widely adopted, by the way. So this neatly shows how the in-memory data, persistence, and indexing all come together in a real system. So what essentially happens here is, so first your data will come inside this to the coordinator node. So this will send this to the streaming nodes. So streaming nodes is nothing but your RAM, which we were discussing. And the durable storage you see on the right side, that is your persistent storage. That's a disk. Our job is to make sure that this RAM does not get bombarded with more and more data. So we have to periodically send these data to this durable storage. So this process is what we call as flushing. But even before doing all those, so first thing is you're going to insert the data in the streaming nodes. Along with it, you are also going to record that, okay, this is the data ID and this is the operation which was meant to happen in something called write ahead logs. This is for durability because during insertion it might fail. And now once it's got inserted, I'm going to wait until a threshold of segment reaches. This threshold can be, just say for example, 10 data points. Until 10 data points comes in, I'm going to wait. So once the threshold reaches, then I will flush this segment to object storage. And this is done in two ways. So you can't simply push this data set to this object storage. You first have to index it. So but the one problem comes with indexing is that during the process of indexing, your machine can fail. So what we do is, before starting this indexing process, I'm going to record that, okay, for this segment, there are 10 data points and these are the data points. And I will put it in something called bin logs. So that even if your indexing fails, you can replay this logs and again rekindle your machine and continue your process. So now that we have pushed this indexed data, and the way we, okay, once your indexing process is over, you're going to seal the segment. You're going to make this as immutable, only read only. You're not going to update that anymore and push that segment to object storage. So during your querying time, your query nodes is going to ask coordinators that fetch me the relevant sealed segments for my query vector. And that's going to give you segments back from durable storage to your RAM. The full dotted line is RAM. So in this way, we will be able to do querying more efficiently. And also there's something called compaction, so which happens in the background where you have multiple small sealed segments and you don't need this to keep growing. So you're going to do a re-indexing, meaning you're going to combine these small sealed segments into big segments. In that way, your query will have less coordination overhead. So this is Milvus. Okay, next is hybrid search, which is lexical plus vector search. So, okay, why do we need hybrid search in the first place? Yeah, we have talked about only vector search in isolation, right? But in real world application, context matters too, not just semantic matters, but also context awareness matters. So this is where hybrid search comes in. So where we combine both the power of vector similarity and the traditional filters or keyword search. So I'm taking an example for open search database hybrid search. So what does this do? This will do both lexical search as well as KNN scoring search. And these two scores will vary. Your KNN score is going to be 0 to 1. Lexical score is going to be 1 to infinite. So you are going to normalize this first, make it into the same vector scale, and then you're going to combine the score, put it in a list, sort this list, get the top K documents. So I'm here showing some demo on these three searches. So first is lexical search, keyword search. Say for example, I am typing women's shoes and I am getting 5 results out of this. So out of the 5 results, what I got was 3 were men's shoes. I think, yeah, now it will run. Yeah. So out of the 5 searches, 3 were men's shoes and 2 were women's shoes. So even though it was able to properly match with the women's shoes, but just because the word shoes there in men's shoes also, it was able to give that as a result. So in this case, you're not really minding the user and giving other unnecessary results. Okay, let's say what a vector search does. So the same I'm searching. In this case, it gave me 5 women boots shoe. And boots, yes, they are shoes, but I'm not giving a variety of shoes for the customer. So this is why you need a hybrid search. So where it, in this case, it gave 2 women's shoes, which are not boots, and 3 boots from the vector search. So you are essentially doing both context awareness and as well semantic awareness. And let me quickly go to the performance optimization ecosystem. So you have key metrics which you can use to say measure your accuracy of your database. There are some trade-offs and index parameters. These things we have all discussed. And there are some optimization strategies like you can align the index type with workload characteristics. So based on your workload, I just told you, right? Choose the right algorithm. Don't just blindly go for something and use hybrid storage tiers. So like frequently cached data will be in hot data and then it follows by warm and cold. Parallelism, compaction, caching, and you also have to monitor this continuously. Open source database offers this monitoring. And ecosystem landscape, you both have open source and as well as managed platforms. Also, you can integrate this with LLM frameworks. Some closing key takeaways. Sorry for taking a long time to come to the slide. So VectorDB or the backbone of RAG system. So choosing the right ANN index depends on your workload speed, accuracy trade-off. Also true performance comes from architecture, not just algorithms. It also is more to it, which we saw. And also hybrid search is going to power your real world applications and always design for your workload, not for the hype. Thank you. And these are my references. Yeah, you can refer to this. Thank you. Any questions? Hey, thank you, Kumar. I thought half the people slept off, but okay, that motivates.
We are nearing the end of the session. If you have more questions, you can ask us in this chat. It'll be open for some more time. We'll move on to the next one. Say, before you close, before you start leaving, all I would like to say is we have a meetup Techceleration channel, Techceleration channel meetup. The link will be posted in the chat window. You can look up. This video would be featured in YouTube so that you can trace back this, and you can also reach out to the speakers in their LinkedIn profile and chat with them and connect and interact more. I hope you've had good takeaways from scalable agentic RAG to a Comet-like system built in mobile, and how marriage between architecture and algorithms is important for a good vector DB family. All that you must have had as takeaways. Thank you all for your time. Thank you for spending a time on a weekday. Hope we meet you soon in the next edition, the 24th edition, hopefully in physical, in person. Thank you. Anybody had a question? Let's unmute you, Nandini, so that you can ask a question, and we'll end with that. Could somebody unmute Nandini? Sundar, would you like to take up this question? Yeah, anybody would like to take up this question? Come. One second, let me show that question itself. Mic is still blocked for her. You are unmuted, Nandini. Could you try it again?
Yeah. Now it's mic is unmuted. So my question is like, so whenever we try like RAG applications, we want to test it out with the relevancy test and accuracy, right? So most of time I just go with the RAGA's score based. So it's mostly about the fates and the retrieval part. And along with that, I also seen like a golden retrieval method where we can have a query and along with the responses. So these are the things that I mostly tried out. And I guess like the golden retrieval data sets is more good while comparing with Raga's score test. So just want to make sure like, is there any other advanced method where we can do check, especially when it comes to like a domain specific?
Some of our team members have done Ragas and Golden Retriever method. They're unable to hear you fully.
Is my
we will
voice?
answer
Yeah, okay.
We'll answer the question in chat, Nandini. Sorry about this.
Yeah, sure.
Yeah.
Okay.
But yes, some of them
Thank you.
have worked on Ragas and Are there other evaluation framework for RAG systems? We'll come back to the response in the chat. Okay. Thank you for this question. That's it, Anita. Maybe we can conclude the session.
Yeah, sure. Thank you, Sandeep. Thank you all.
Thanks, everyone. Take care. Bye.